Let's touch on the diagnostics of ITCZ transients, which basically goes back to the budget terms in the absolute verticity that we talked about that is needed for creating the inertial instabilities. We are looking here again, by the way, in the previous podcast for figure 1320, I said it wrong. The left panel showed humidity and vertical motion or some such thing. So if I go back here, yes, so this was stream function and humidity. I think I said it as heating rates. Heating rates are actually here. Okay, so these three are basically the humidity building up and being pushed, advected up by the convection, and this shows the heating rates. Okay. In the diagnostic of ITCZ transients, then again look at the time latitude diagrams for the same construct as before, with peak convection at 7.5 north 6 days before and 6 days after. And for the same section, look at the vector velocity fields and the divergence lines, as well as the budget terms in terms of delta OLR and delta ADA. So these are filtered at the 4 to 8 day time scale to see how the balance of verticity happens. The main story is again that you can clearly see the OLR convection from the previous cycle dying out, building up to the current cycle, and then dying out in terms of the OLR, and the corresponding movement of the verticity lines, especially the zero verticity line and the negative and positive verticity lines on either side. And you can see the patterns here of convergence and divergence. So we are talking about basically the advection of the absolute verticity and vertex tube stretching. Okay, so the main point is the same as we made before. If we look at convection and the verticity lines, there is a phase relation between them, and the terms of advection and stretching, tube stretching, are both contributing to the balance of verticity, especially over near north of the zero line, as we talked about before, which is consistent with all the other features we talked about the divergence convergence doublet and the role of the or generation of the westerly winds north of the zero absolute verticity line, which is also needed for, and the meridional shear that are needed for verticity balances. Okay, so just that's a good way to close that piece out. And this is now showing 500 hectopascal. So this was 925 lower level. This is in the mid troposphere, showing relative humidity and the V lines, and again the close correspondence at these transient timescales are an indication of the circulation dynamics that is needed to do the vertical structure of the convection, moisture loading, and verticity balance. Okay. With that, let's go briefly to the origin of easterly waves. Easterly waves typically were called African easterly waves, and many people still refer to them as African easterly waves. And you can see the brief dynamics here in terms of pressure versus latitude, and this is done across 5 East, which cuts through West Africa into Sahara. So you can see the lines here of change in the gradient of Q along an isentrope. So these are the isentropes 300, 310, 320 and 330, and the red lines, blue shading denotes the westerlies. Okay, so you have the westerlies in just to the south of the ITCZ that we talked about before, or was it not? Just check and make sure. And the isentropes appear as dashed lines. Yellow shading encloses regions where you have easterly winds greater than 5 meters per second. So you have change in winds and a strong shear here. Red contours show isentropic potential vorticity field in PVU units. The change in gradient of Q along an isentrope to the south of the low-level easterly jet. So there is this folding of the PV line that shows the change in gradient. And Charney had again already done some work showing that if you look at the meridional gradient of the absolute vorticity, which we saw before, Q is minus G eta theta d theta dp, which we wrote as zeta theta isentropic relative vorticity plus planetary vorticity, and we had written that in terms of the meridional shear, which is relevant for this wind field that we are looking at from the surface to the height. So this is the low-level easterly jet. So essentially, when dq dy changes sign in the domain, then that creates instabilities, which is what which is why this change in gradient is very critical, where you get instabilities which are then propagated westward as easterly waves. And this was considered to be the place where these originated, and people even argued that they are carried across the Americas into the Pacific. We have been looking at easterly waves in the Pacific in the example of transient in the ITCZ, for example, but it turns out that actually those easterly waves in the Pacific and also in the Indian Ocean are not necessarily related to the generation mechanisms in the West African region with the strong PV gradient. Okay, they are independently generated, which probably helps us explain the things that we didn't explain before in terms of a lack of strong cross-equatorial pressure gradient in the central western Pacific, with zero absolute vorticity line being close to the equator and yet having off-equatorial convection, which is different than the strong gradient and the absolute vorticity line migrating northward across the equator, creating inertial instabilities and so on. So this, however, can be probably explained in terms of the easterly waves that are generated here by similar mechanisms as in the West Pacific, and those bringing in instabilities into this region to drive convection. So not local inertial instabilities related to the absolute vorticity migration, advection, but remote forcing from the easterly waves. That would be consistent with the westward propagating features that Holton was talking about when it came to ITCZ that we discussed before. Okay, so easterly waves are critical. Typically they come up in the Atlantic in terms of their strong association with cyclogenesis. So usually when cyclones are born, converted into tropical depression, and then category 1, 2 and so on, there is always some relation with the easterly wave activity. You typically need vorticity and mid-tropospheric humidity for driving tropical disturbance into a depression and grow further into a hurricane or a cyclone, of course with the available ocean energy and so on. So there is that relation, but here mostly it can be used to say that maybe the unexplained situation here is more related to the remote forcing from the easterly waves. Okay, we'll come to the southern hemisphere and the great cloud bands that we mentioned several times and see how those work given all the dynamics that we have been talking about thus far.